Today we'll be looking at the problem shortest subarray with OR at least K2. This is a problem featured in Biweekly Contest 127. It's a little bit tricky with some of the bitwise logic here, but hopefully this explanation makes sense. So the question reads, we're given an array nums of non-negative integers and another integer k. An array is called special if the bitwise OR of all of its elements is at least k. And let's quickly just go over what exactly bitwise OR is. So say we have two numbers, let's say 1, with its binary representation being 0, 1, and we have 2, with its binary being 1, 0. The bitwise OR of this operation would be the operation denoted by the pipe symbol. And basically what this means is we're going to look at every position. If there is at least 1, 1 in this position, then the final result of that position will be 1. So we do that for this first position. Similarly here, for the second position, we do 0, 1, and we have 1. So this final binary will actually equal 3. Let's do another example. So say we have 3, 1, 1, and we do a bitwise OR of 5, which is 1, 0, 1, right? So do the same logic here, 1 and 1. Doesn't matter if there's more than 1, as long as there's at least 1. We do 1, 1, 0, 1, 1, 0, 1. So this binary actually equals 7. So what you can kind of notice is that when we do an OR operation, the final result will always be greater than or equal to the previous number, right? So say we're going through a list of numbers and just kind of like adding up all the bitwise ORs. We know for a fact that the values in this array will continue to rise or remain equal. There's no chance they will ever go down. Because with bitwise OR, we are always adding bits and never removing bits. So, given the fact that we want to return the length of the shortest special non-empty subarray, one idea that might immediately come to mind is sliding window. So, sliding window, I won't go super in-depth with it here. There's tons of videos on YouTube. But when we have shortest, sliding window is a great candidate. So what we can do is say, have 2 pointers. We'll kind of extend our right pointer until we meet some condition, right? When we meet our condition here, we can start shrinking the left and removing pointers here, shrinking that window while that condition is still met. And our condition here is the elements are at least k, right? So we can keep moving elements to the right until this condition's met. So at this point, you might be asking, say we see a number, we OR it, it's greater than or equal to k. Should we continue moving the right? Well, no. As we said, looking at this, we know that if we keep adding elements with this OR operation, our values will always be at least equal or greater than what we have now, right? So we know that we're going to have the same condition met, but our arrays will just keep getting larger and larger and larger. What we want to do is actually, once we meet this condition, say, okay, can we shrink this window and make it smaller, right? So that's kind of the idea behind the sliding window. So let's look at a more specific example here. So we're going to take the array 1, 2, 32, 21, and our k value here is 55, right? So again, what this means is we want to find the shortest subarray where the OR value of all the elements is at least 55. So here I've written out the binary representation of all these numbers. We can kind of just start going through it. So 1 and 2, this is pretty simple. What we're going to end with here is 0, 0, 0, 0, 0, 1, 1 after we do this operation. And again, if you need to review what this operation is, you can rewind the video and go back. But this value actually will end up equaling 3, right? So then we'll move on to 32, and we're going to say, what is the OR of 32 and 3? So you can see here our OR is 1, 0, 0, 0, 0, 0, 0, right? And then our OR operation of these two will be 1, 0, 0, 0, 0, 1, 1. So this equals 32. This is another 2, which will be 34, and 35. So now we have 35, right? Then we're going to do the OR value of this with 21. So we have 0, 0, 1, 0, 1, 0, 1. So we'll do the OR value there. We'll have 1, 1, 1, 0, 1, 0, 1. So what this value is 55. So you notice that 55 is the same as what we have here, right? So we can see that once we did the OR of all the elements in the subarray, it met our condition of 55. So at this point, we found a minimum length of 4. Now, given the sliding window, we want to say, okay, so we found a valid subarray here. Let's shrink our left value and see if, as we shrink it, our case remains valid. However, this becomes kind of tricky, right? These operations, bitwise, and, and OR, are actually, these are destructive, right? What that means is when we apply them to a number, it's almost impossible to undo it. Like you could try doing the complement, you can do exclusive ORs, like all these different tricks, but unfortunately, you're never going to be able to take a number and get it back to its original value after having done that OR. So this is kind of an issue, right? Because we can't actually shrink these values and take them off of our window. How are we going to do this with our current iteration? So what we actually need to do is, as we're going through this list, we actually want to keep a count of all the bits that we've set so far, right? So imagine we're using some 32-bit numbers, right? So if we have an array of length 32 that just kind of keeps track of all of the bits that we've seen, and we'll see what that looks like. So say we have 1, right? As we go through 1 and check its bits, we'll say, okay, we know that in the first position for 1, right here, we'll have a bit set, right? So we can add 1 here, do the same thing for 2. We see for 2, we have 1 in the second set, so we can set it here. For 32, here, so we'll put it here somewhere, similar here. So here we'll have 2 set, we'll have 1 set. So we're basically just kind of going through all these numbers, and we're keeping track of what bits we have set, right? So you might be thinking, how does this help us? Well, when we find this window, right, and we want to start shrinking, what we can do is look at this left element. When we see this element, we know what bits are set in it, right? We can use this element and figure out what bits are set. So what we can do is say, all right, let's look at 1. All the elements which are set, let's just subtract 1 from there, right? So here we have 2 1-bits set. So this would now become 1, right? And obviously 1 only has 1 bit set, so we would just, that would be the end. Let's look at 2 also. We can remove 2 effectively by saying, all right, all the bits that are set to 1 for 2, let's remove them here. So we can remove them here, and this becomes 0. This is the interesting case, right? We see that when we remove the 2, effectively this bit becomes nullified, not set for our entire number. So what can we do with this? Well, we could say basically this bit value represents 2. This represents 1, 4, etc. So we see this was previously set, and now it's not set, right? So basically what we could say is our value now would be this minus whatever bit value we just removed, so 53, right? So this is kind of the tricky part, is realizing you have to do this logic of keeping track of the bits and updating this bit table as you kind of go through and look at the sliding window. So otherwise, this is a very, very kind of straightforward sliding window problem, but figuring out this logic of the bit table can be quite confusing. So we do have to, for every number, when we either add it to our bit set or remove it, go through 32 bits, right? Fortunately, overall, we're only going through each number one time, or at most twice, rather, to add it and remove it. So it's an O of n operation times 32. The 32 will cancel out. So overall, doing this, even with this bit table, will be an O of n operation. So let's hop over to the code and kind of show you how all this actually works. So for this solution, it was actually a lot cleaner for me to add a couple helper functions. So the first one is called update bits. Basically what this will do is take in some current number. It'll take in that bits array that we described in the solution previously, and also a Boolean flag. And this Boolean flag will tell us whether we're adding bits to our bit set or we are removing them. So what we do in here is basically we just go through all the possible bits that could be set for this number. And basically, if the add is true, we're going to add 1 if that bit is set, or 0 if it's not set. Otherwise, we'll subtract 1 if it's set, and 0 if it's not set. Then, essentially what we're doing is we're shifting all our bits to the right. And what that helps us do is, say we looked at the bit in the rightmost position, we checked if it's set or not, and now we're moving everything to the right so we can check the next one. And we basically just do this for every possible bit in here. We have another helper function called bits to number. Basically what this does is it just goes through all the bits in that bit array and says, if it's set, we know that we need to add the value of that bit into some number representation. So we check if it's set, and this is just a shorthand for saying we want to take 1 and shift it over I number of bits. We add it to our result. This will just take that bit set and return this result number here. So then after this is just a very, very simple, pretty much textbook sliding window problem, right? We have our left and right pointers. We have our minimum length, which is the minimum answer that we found so far. And then we have our bits table where we keep track of the bits. So then we'll just do the sliding window. So while right is less than the length of nums, we're going to update the bits with that number at the right index. So then here's the part where we've met our condition and we want to shrink the window, right? So while that number is greater than or equal to k, we're going to update our min length because we found a valid answer. We're going to update that bits, but notice we are passing in false, which means we are removing bits that we found from that bits table and then incrementing our left to shrink the window. After we've done all this and our window is no longer valid, we're going to move to the next element. So we do one other loop at the end here. And basically what that's doing is saying, if we've reached all the way to the right end of the array, we still want to shrink our left just to see if there's any other smaller possible subarrays that we've missed and update our logic. So basically exactly what's happening in this loop, we're going to do at the end as well. Then what we're going to do is if our minimum length is equal to float infinity, what that means is we have not actually found any subarrays which meet our condition. So we return -1. Otherwise, we're going to return our min length. So let's submit that and make sure it works. And it does. Well, yeah, this is a pretty interesting problem. I hope this was helpful and kind of made sense. And thank you for watching.